Sharks are incredibly successful animals, having existed since long before the time of the dinosaurs and making it through several devastating mass extinction events. There are many reasons for their success, including their ability to adapt and occupy new niches, and the diversity of modern sharks just goes to show how well they've been able to do this. Sharks are still offering up all sorts of new surprises too, and although there's much we still have to learn about these amazing fish, the continued research into their biology means that incredible discoveries are frequently being made. One such discovery that was announced recently was the revelation that hammerhead sharks are able to, in a way, hold their breaths in order to dive deeper. This might sound a bit strange, considering that hammerhead sharks are fish and therefore extract the oxygen they need from the water and aren't required to return to the surface to breathe like marine mammals such as whales and dolphins are. However, there are some surprising similarities between these sharks and those marine mammals, it turns out. Hammerhead sharks, in this case specifically scalloped hammerhead sharks, the species Sphaerina lewini, mostly live in relatively shallow, tropical warm waters where temperatures tend to be in the range of about 26 degrees Celsius. However, the prey that make up a significant part of their diet, including certain types of fish and squid, live in the bathypelagic and mesopelagic zones, much deeper down. So, in order to access these prey items, the hammerheads must dive. Diving in fish, which do not come to the surface to breathe air, is defined as periods of vertical movements that begin and end in shallow waters. And in the scalloped hammerheads, these are recorded as movements starting and finishing at depths of under 100 meters and exceeding 400 meters. Well, as you might imagine, when these animals dive down, they encounter much colder water temperatures as they go, reaching lows of 5 degrees Celsius. This is a problem faced by any deep diving animal. However, it's more of a problem for ectothermic animals, those organisms that rely more on their environment to maintain their internal body temperature, such as hammerheads. Deep diving mammals such as whales are endothermic and are capable of regulating their internal body temperature. And along with other anatomical adaptations to coping with the cold, including extensive layers of blubber, they are very capable of operating at depth. Another problem faced by fish is the fact that their gills, which are very efficient at exchanging oxygen with the water, also happen to be particularly good at transferring heat too. This means that colder waters can cause rapid cooling of the fish's body, with metabolic heat from muscle tissue being transferred by blood circulation to the gills, where it is then lost to the water, which is obviously not ideal for deep diving as they'd be at risk of damaging their internal organs due to this rapid heat loss. Many other fishes that inhabit the epipelagic zone of the ocean have found ways of managing this heat loss, with regional endothermy evolving in some groups such as the lamnid sharks, including white sharks, makos, porbeagles and salmon sharks, and in tunas. Regional endothermy allows the temperature of certain parts of the bodies of these fish to be internally regulated through the use of countercurrent heat exchangers that enable specific organs and tissues to be kept warm. These heat exchangers are essentially just blood vessels with warmer blood flowing in the opposite direction to a nearby vessel with colder blood, exchanging heat energy as they pass and warming up that cold blood, resulting in the maintenance of temperature of certain parts of the body. Another way heat loss through the gills has been solved when swimming in colder waters can be seen in whale sharks, which just grow to such huge dimensions that they are able to retain enough heat due to their large body mass and the slower rate at which they lose it, a condition known as gigantothermy. But then what about the scalloped hammerheads? They aren't regional endotherms and they're not big enough to be gigantotherms. So how do they manage the heat loss when they dive? Well, that's what this new discovery is all about. A team of researchers attached remote logging devices to adult individuals that could record water depth, ambient temperature, rates of activity in the sharks, the orientation of the individuals, and core muscle temperature. They then recorded over 100 separate dives and found something very interesting about these sharks. The hammerheads were experiencing very cold temperatures during the deepest stages of their dives, and yet the logging devices didn't record any significantly rapid body temperature drops during the descent and bottom stages. The only significant decrease in body temperature occurred on the final ascent phase as the sharks neared the surface waters again. The exact reason for the surprisingly constant body temperature held by these sharks as they dive isn't known for certain, but the researchers have a pretty good idea of what might be going on. They suspect that the hammerhead sharks are actually holding their breath as they dive, and there's some pretty good evidence to support this. It seems as though the sharks are closing their gill slits and mouths when they dive into colder waters, stopping their gills from being exposed to water flowing over them and completely halting the process of extraction of oxygen from the water. Of course, this also has the effect of stopping heat transfer too, so these sharks are quite literally holding their breath as marine mammals do. The researchers explain how the body temperature regulation can't really be explained any other way. If the transfer of heat at the gills was continuous throughout the dives, meaning the gills were still functioning as normal, then we'd expect to see a body temperature decrease starting during the deep phases of the dive. But that's not what's happening. Instead, the temperature is maintained until the very end on the journey back up. So they must be doing something to alter the normal function of their gills. It's possible that a significantly lowered heart rate could also reduce the rate of cooling, or the shunting of blood away from the gills, but there's currently no evidence for true vascular shunts at the gills of any sharks. Instead, it seems the simplest explanation is that the sharks are just closing their gills, and then the body temperature decrease on the ascent represents the gills opening up again. Some video evidence may also support this, as there's footage from a remotely operated vehicle at a depth of over 1,000 meters showing a scalloped hammerhead that seems to have closed gill slits. The researchers write that more data is still needed to fully confirm this hypothesis though, and suggest attaching cameras to the pectoral fins of the sharks that could record the gills opening and closing. This discovery also has some interesting implications for the limitations of deep diving in fish. Before this revelation, it was thought that heat loss was the main limiting factor that dictated the duration of dives. But it might be that oxygen demand is more of a limit instead, meaning the comparisons to breath holding and marine mammals are even more accurate. The next question then is how the hammerhead sharks are able to be such active hunters while on these deep dives, as they must be building up a significant oxygen debt. Perhaps they also have extensive oxygen stores in their tissues and blood and are capable of dealing with the buildup of substances resulting from anaerobic respiration. Another interesting line of inquiry is whether this gill slit closing technique is happening in other sharks and fishes that deep dive, as it does appear to be a pretty effective solution to the heat loss problem, and it wouldn't be surprising if it has arisen multiple times in various lineages. So there we have it, a remarkable instance of how sharks continue to surprise us with their adaptable biology, and how evolution can result in some pretty elegant yet simple solutions to physiological problems. I'll definitely be keeping an eye on this line of research to see what becomes of it, and whether or not we're able to get some direct video evidence of the gill slits closing. And I do wonder how widespread this behaviour might be among fishes. It's very interesting to think about. Anyway, I really hope you've been enjoying Shark Week 2023 so far. I still can't believe this is our 6th one now. We've got some fantastic videos still to come, including an episode dedicated to the wonderfully bizarre goblin shark, a bonehead shark special, our fossil hunting trip to find some shark teeth of our own, and of course the Megalodon video to finish the week off with. This time looking at Megalodon's competition with the fearsome sperm whale Leviathan. Anyway, thank you for watching, and a big thank you to our Patreon supporters, especially our Dinosaur tier supporters, Amanda von Nordek, Clara Middleton, Daniel Ingraham, Dhruv Shrivastava, Gary Arrington, Giortist, Greg Silvernail, Corey Peterson, Loxypoo, Mark Nevin, Mendicant Fryer, Mike Pace, Monitor Man, Persian Boy, Ralph Balzac, Robert Thomas, and Steve Bradshaw. If you would like to find out more about our world, its history, and the wonderful life that surrounds us all, please feel free to subscribe to the channel if you think we deserve it, and if you would like to see more from us.